Hello students, welcome to this lecture 1 Permutations and Combinations. In this lecture, we will cover NCERT examples 9 to 9, 10 to 19 and NCERT section 6.4. This is disclaimer. First, we will solve some NCERT examples and then we will discuss NCERT section 6.4. So let's get started. So look at example 10. So these examples ask us how many 4-digit numbers can be formed by using the digits 1 to 9 if the repetition of the digits is not allowed. So the question is asking us to find 4-digit numbers that can be formed by using the digits 1 to 9 if repetition of the digits is not allowed. Here we have given 4-digit numbers that can be formed by using digits 1 to 9 with no repetition. So here order matters. For example, 1 2 3 4 and 1 3 2 4 are two different numbers. They are not same number. Here we need to arrange 4 digits from 9 digits. Okay, so therefore there will be as many 4-digit numbers as there are permutations of 9 different digits taken 4 at a time. So now the formula for permutations is NPR. This is equal to n factorial upon n minus r factorial. So in this case, we have n is equal to 9 and r is equal to 4. So 9PR is equal to 9 factorial upon 9 minus 4 factorial. This is equal to 9 factorial upon 5 factorial. Now we can write 9 factorial as 9 into 8 into 7 into 6 into 5 factorial. As we know, n factorial is equal to n times n minus 1 factorial. Okay, and then we can simplify it and we get the value of 9PR. So here 5 factorial cancelled and 9p4, this is equal to 9 into 8 into 7 into 6. Now after multiplying, we get the answer is 3024. Therefore, the number of 4-digit numbers using digits 1 to 9 with no repetition is 3024. So I hope this example is clear to all of you. So now let's move to the next example. So in this example, we have to find number of numbers lying between 100 and 1000 can be formed with the digits 0, 1, 2, 3, 4, 5 if the repetition of the digits is not allowed. Okay. So the question asks us how many numbers lying between 100 and 1000 can be formed with the digits 0, 1, 2, 3, 4, 5 if the repetition of the digits is not allowed. So let's look students here. Here we need to make 3-digit numbers can be formed with the digits 0, 1, 2, 3, 4, 5 between 100 and 1000. Okay, so it's important to understand that repetition is not allowed here. So now calculate total permutation. So 6p3, this 6 digits second, 3 at a time. Okay, this means the permutations excluding 0 in 100 place. Okay, so here we need to pay attention that 0 cannot be come in the 100 place. So therefore we will calculate permutations 5p2. So meaning we need to arrange 2 digits from 5 digits. Okay, now let's apply the formula 6p3 minus 5p2. This is equal to 6 factorial upon 3 factorial minus 5 factorial upon 3 factorial. As we know the formula, NPR is equal to n factorial upon n minus r factorial. Look, now simplifying, okay, factorials. So here we will use the property n factorial is equal to n times n minus 1 factorial. Okay, so it will give us 6 into 5 into 4 into 3 factorial upon 3 factorial minus 5 into 4 into 3 factorial upon 3 factorial. Okay, so now here 3 factorial will be cancelled to each other. So here we are doing the final calculation. So this is equal to 6 into 5 into 4 minus 5 into 4. This is equal to 120 minus 20 is equal to 100. Therefore, the numbers lying between 100 and 1000 using digits 0, 1, 2, 3, 4, 5 with no repetition is 100. Okay, so this is the final answer. I hope it is clear to all of you. So now let's move to the next example. In this example, we have to find the value of n such that np5 is equal to 42 into np3 where n is greater than 4. Okay, and in second part we have np4 upon n minus 1 p4 is equal to 5 by 3 when n is greater than 4. Okay, so let's find the values of n here. So let's start the solution step by step. Look students, here we are given that np5 equal to 42 into np3. Using the formula npr is equal to n times n minus 1 into n minus 2 into dot 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 n minus r plus 1. So we have n times n minus 1 times n minus 2 times n minus 3 times dot dot n minus 4 equal to 42 times n into n minus 1 into n minus 2. So let's solve this equation. Since here n is greater than 4, this means that the value of n should be greater than 4. So n times n minus 1 times n minus 2 does not equal to 0. Therefore, by dividing both sides by n times n minus 1 times n minus 2, we get n minus 3 times n minus 4 is equal to 42. Okay, this has become a quadratic equation. It implies n square minus 7n minus 30 equal to 0. Okay, so this is a quadratic equation that needs to be solved, and it implies n times n minus 10 times n plus 3 equal to 0. Okay, from this we will get the possible values of n. It implies n is equal to 10 or n is equal to minus 3, but we were given the condition that n is greater than 4. Okay, so here n is equal to minus 3 is invalid. Here we will take the value of n is 10. So as n is equal to 10 is the only valid value, so the final answer is n is equal to 10. I hope this part is clear to all of you. Let's look at the solution to the second part of this example. So given that n p4 upon n minus 1 p4 is equal to 5 by 3. Using the formula npr is equal to n times n minus 1 times n minus 2 times dot 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 n minus r plus 1. So using this formula, we can simplify it, okay, and we will get the value of n. So we have 3n times n minus 1 times n minus 2 times n minus 3 is equal to 5 times n minus 1 times n minus 2 times n minus 3 times n minus 4. Now cancel out n minus 1, n minus 2, n minus 3. Okay, multiplied n minus 1 into n minus 2 into n minus 3, and we get 3n equal to 5 times n minus 4. Okay, since here n minus 1 times n minus 2 times n minus 3 not equal to 0. Since we have given the condition n is greater than 4, it implies 3n is equal to 5n minus 20. Now we will rearrange it and we will get 2n equal to 20. So after simplifying, we will get the value of n is 10. So the final answer is 10. Okay, therefore n is equal to 10 is the correct answer here. Now this question asks us to find the value of r when the equation is 5 times 4pr equal to 6 times 5pr minus 1. So here let's find the value of r. So given that 5 times 4pr equal to 6 times 5pr minus 1. So we need to solve this equation. So we have 5 times 4pr. Okay, and as we know the formula npr equal to n factorial upon n minus r factorial. Okay, so this gives us 5 times 4 factorial upon 4 minus r factorial is equal to 6 times 5 factorial upon 5 minus r plus 1 factorial. Here we are simplifying factorials. So look, we use here n factorial equal to n times n minus 1 factorial. Okay, to further simplify the equation, and it gives us 5 factorial upon 4 minus r factorial is equal to 6 times 5 factorial upon 5 minus r plus 1 times 5 minus r times 5 minus r minus 1 factorial. It implies 5 factorial upon 4 minus r factorial. This is equal to 6 times 5 factorial upon 6 minus r times 6 minus 5 minus r times 4 minus r factorial. Now cancel out 5 factorial and 4 minus r factorial. We get 6 minus r multiplied with 5 minus r is equal to 6. Let's now see further calculation. So it implies r square minus 11r plus 24 is equal to 0. So this is a quadratic equation, and now let's solve this equation. Now factorize and we get r minus 8 times r minus 3 equal to 0. It implies r is equal to 3 comma 8. In NPR, this is equal to n factorial upon n minus r factorial and n greater than equal to 4r. Okay. Therefore, r is equal to 3. Okay. So the final answer is r is equal to 3. I hope this example is clear to all of you. Now, look at example number 14. So this question asks us to find the number of different 8-letter arrangements that can be made from the letters of the word daughter so that vowels occur together. Okay. And the second part, vowels do not occur together. So let's solve this example. So let's start the solution. There are 8 different letters in the word daughter, in which there are 3 vowels, namely A, U, E. Since the vowels have to occur together. Okay, so assume here them as a single object. So here we take single object A, U, E. The single object together with the 5 remaining letters will be counted as 6 objects total. Then we count permutations of these 6 objects taken all at a time. This number would be 6p6. This is equal to 6 factorial, since npn is equal to n factorial. Now, corresponding to each of these permutations, we shall have 3 factorial permutations of the 3 vowels A, U, E taken all at a time. So, students, here we will get the number of different 8-letter arrangement that can be made from the letters of the word daughter, so that all vowels occur together. For that, we will apply multiplication principle. Okay, so we know while we will know the multiplication principle rule. Okay, if there are m ways to perform one task and n ways to perform another task, then there are m into n ways to perform both tasks together. Therefore, how many numbers of different 8 letters arrangement that can be made from the letters of the word daughter, so that all vowels occur together? So therefore, the answer is basically 6 factorial into 3 factorial. Okay, this is equal to 4320. So the number of permutations when all vowels occur together are 4320. So look, students, here, second part of this example. So if we have to count those permutations in which all vowels are never together. Okay, so let's calculate how many numbers of different 8 letters of arrangements that can be made from the letters of the word daughter, so that all vowels do not occur together. So we first have to find all possible arrangements of 8 letters taken all at a time, okay, which can be done in 8 factorial ways. Then we have to subtract from 8 factorial, okay, the number of permutations, 6 factorial into 3 factorial, in which the vowels are always together. So therefore, the required number is 8 factorial minus 6 factorial. This is equal to 6 factorial times 7 into 8 minus 6. Since n factorial, this is equal to n times n minus 1 factorial. This is equal to 2 times 6 factorial times 28 minus 3. And this is equal to 50 times 6 factorial. And this is equal to 50 into 720 equal to 36,000. Therefore, the number of permutations when all vowels do not occur together are 36,000. I hope this is clear to all of you. So now let's move to the next example. The example is, if we have 4 red, 3 yellow and 2 green discs be arranged in a row. Okay, so in how many ways 4 red, 3 yellow and 2 green discs be arranged in a row if the discs of the same color are indistinguishable? Okay, indistinguishable. So let's find in how many ways we can do it. So let's start the solution. So given that 4 red, 3 yellow and 2 green discs be arranged in a row, the total number of discs are 4 plus 3 plus 2 equal to 9. Out of 9 discs, 4 are of the first kind. Okay, that means the first kind is red here. 3 are of the second kind, that are yellow, and 2 are of the third kind, that are green. Now, using theorem 4, that the number of permutations of n objects where p1 objects are of the first kind, p2 are the second kind, and dot 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 pk are the kth kind, and the rest of any objects are of the different kinds. Okay, that is n factorial upon p1 factorial into p2 factorial into dot 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 pk factorial. So then the number of arrangements is 9 factorial upon 4 factorial into 3 factorial into 2 factorial. Here n is 9, p1 is 4, p2 is 3, and p3 is 2. This is equal to 9 into 8 into 7 into 6 into 5 into 4 factorial upon 4 factorial into 3 factorial into 2 factorial. This is equal to 9 into 8 into 7 into 6 into 5 upon 6 into 2. This is equal to 1206. Therefore, the number of permutations where 4 red, 3 yellow, and 2 green discs are be arranged in a row are 1206. I hope this example is clear to all of you. Now, this example is asking us to find the number of arrangements of the letters of the word independence. In how many of these arrangements do the words start from P? So let's start the solution of the first part. Given that the letters of the word independence, there are 12 letters in which N appears 3 times, E appears 4 times, and D appears 2 times. Okay, and the rest are all different. Now, we will use theorem 4. The theorem 4 states that the number of permutations of n objects where p1 objects are the first kind, p2 objects are the second kind, and the pk are the kth kind, and the rest of any other different kinds is n factorial upon p1 factorial into p2 factorial into dot 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 pk factorial. Number of arrangements is 12 factorial upon 3 factorial into 4 factorial into 2 factorial. Since here n is 12, p1 is 3, p2 is 4, and p3 is 2. So here we are calculating total arrangements using the formula n factorial is equal to n times n minus 1 factorial. So this gives us 12 factorial upon 3 factorial into 4 factorial into 2 factorial. This is equal to 12 into 11 into 10 into 9 into 8 into 7 into 6 into 5 into 4 factorial upon 4 factorial into 3 factorial into 2 factorial. This is equal to 12 into 11 into 10 into 9 into 8 into 7 into 6 into 5 upon 6 into 2. Since 3 factorial is 6 and 2 factorial is simplifying the calculation gives 12 into 11 into 10 into 9 into 4 into 7 into 5. Okay. This gives us 1663200. Therefore, the number of permutations of the word independence is 1663200. Let us fix P at the starting left position. Then we count the arrangement of the remaining 11 letters. So therefore, by using the theorem 4, the number of permutations of n objects where p1 objects are the first kind, p2 are the second kind, and pk are the kth kind, and the rest of any are of different kinds is basically n factorial upon p1 factorial into p2 factorial into the dot pk factorial. The number of words starting with p is basically equal to 11 factorial upon 3 factorial into 4 factorial into 2 factorial. Here n is 11, p1 is 3, p2 is 4, and p3 P2 is 4 and P3 is 2. 11 factorial upon 3 factorial into 4 factorial into 2 factorial. This is equal to 11 into 10 into 9 into 8 into 7 into 6 into 5 into 4 factorial upon 4 factorial into 3 factorial into 2 factorial, since n factorial is equal to n times n minus 1 factorial. This is equal to 11 into 10 into 9 into 8 into 7 into 6 into 5 upon 6 into 2, since 3 factorial is 6 and 2 factorial is 2. This is equal to 11 into 10 into 9 into 4 into 7 into 5. This is equal to 138600. Therefore, the number of permutations of the word independence start with P is 138600. Now, in the second part of this example, it asks us how letters can be arranged when vowels come together. Now look, students, here there are 5 vowels in the given word, which are 4 E's and 1 I. Since they have to always occur together, so we treat them as a single object. Okay. This single object together with 7 remaining objects will account for 8 objects. Then, by using theorem 4 states that the number of permutations of n objects, where P1 are the first kind, P2 are the second kind, and the Pk are the kth kind, and the rest of any other different kind, is n factorial upon P1 factorial into P2 factorial into dot 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 Pk factorial. These 8 objects, in which there are 3 n's and 2 d's, can be arranged as 8 factorial upon 3 factorial into 2 factorial. So corresponding to each of these arrangement, the 5 vowels A, E, 4E and 1I can be arranged as 5 factorial upon 4 factorial. Therefore, by multiplication principle, if there are m ways to perform one task and n ways to do another task, then there are m into n ways to perform both tasks together. By applying multiplication principle, the number of arrangement is 8 factorial upon 3 factorial into 2 factorial into 5 factorial upon 4 factorial. So this gives us 8 into 7 into 6 into 5 into 4 into 3 factorial upon 3 factorial into 2 factorial multiplied with 5 into 4 factorial upon 4 factorial. This gives us 8 into 7 into 6 into 5 into 4 upon 2 into 5. This is equal to 16800, 16,800. Therefore, the number of permutations of 5 vowels in the word independence is 16,800. I hope it is clear. Now, in the third part of this question, we have to arrange the letters of the word independence and find how many arrangements are there where vowels never occur together. Let's see the solution of the third part. So we got 12 factorial upon 3 factorial into 4 factorial into 2 factorial is 1663200. Okay. And 8 factorial upon 3 factorial into 2 factorial multiplied with 5 factorial upon 4 factorial is 16800. So the required number of arrangements is the total number of arrangements without any restriction minus the number of arrangements where all the vowels occur together. This is equal to 12 factorial upon 3 factorial into 4 factorial into 2 factorial minus 8 factorial upon 3 factorial into 2 factorial. This multiplied with 5 factorial upon 4 factorial. This is equal to 1663200 minus 16800. And after calculating, you will get this is equal to 1646400. Since we have given 12 factorial upon 3 factorial into 4 factorial into 2 factorial is 1663200, and 8 factorial upon 3 factorial into 2 factorial into multiplied with 5 factorial upon 4 factorial is 16800. So therefore, the number of permutations of the word independence where vowels never occur together is 1646400. I hope it is clear. Now, let's start the solution of the third part. So let us fix I at the left end and P at the right end. So we are left with 10 letters. So now using theorem 4. Theorem 4 states that the number of permutations of n objects where P1 objects are the first kind, P2 are the second kind, and dot 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 Pk are the kth kind, and the rest if any of these different kinds is n factorial upon P1 factorial into P2 factorial into dot 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 Pk factorial. To apply this theorem, the number of arrangements is 10 factorial upon 3 factorial into 2 factorial into 4 factorial. 10 factorial upon 3 factorial into 2 factorial into 4 factorial. This is your 10 into 9 into 8 into 7 into 6 into 5 into 4 factorial upon 4 factorial into 3 factorial into 2 factorial. Since n factorial is equal to n times n minus 1 factorial. And since 3 factorial is 6 and 2 factorial is 2, then it gives us 10 into 9 into 8 into 7 into 6 into 5 upon 6 into 2. This is equal to 10 into 9 into 4 into 7 into 5. And after multiplying, we get 12,600. Therefore, the number of permutations of the word independence begin with I and end in P is 12,600. Okay, I hope this example is clear to all of you. So students, now we will discuss NCERT section 6.4 combinations. Okay, so first we will see definition of combinations. So what is the definition of combination? So let's understand the definition of combination. So a combination is a selection of objects where the order of the selection does not matter. Okay, so let's see how it denoted. So here we will see now key concept of combination. Okay, so here when we choose a group like A, B, C, this is a combination. The order doesn't matter in this case. Whatever you choose, A, B, C or C, A, B, the result will remain the same. Okay, so here order doesn't matter for combination. But here in permutation, order matters. Okay, for example, 1 2 and 2 1. 1 2 and 2 1 are different for permutation. Okay, but in combinations, order doesn't matter. Okay, so here see, combination positions are equal. For example, a 2% team of 3 players X, Y, Z. Okay, so here you can see we need to make a 2% team. Okay, here what it doesn't matter. So X and Y or Y and X are the same. Okay, considered in the same team. So this will become clear with a visual example. In you can see here. Okay, so YZ and ZY are the same. ZX and XZ are the same. Now we will see theorem 5. Okay, so theorem 5 states that NPR is equal to NCR into R factorial. Okay, so this theorem basically for relationship between permutations and combination. Okay, so NPR is equal to NCR into R factorial. So let's look at its proof. Here we deal with selection. Okay, so which means combination. we select R object from N objects, and this can be done in NCR ways. Now arrangement. Now we have selected the objects and we need to arrange them. We can arrange our objects in R factorial ways. Okay, so there we have R factorial ways to arrange our selected objects from N different objects. Now total arrangement. We use the multiplication principle. If there are m ways to do one task and n ways to do another task, then there will be m into n ways to do both tasks. Okay, similarly, we combine selection and arrangement this way. So the total number of arrangements of R objects from n is the product of the number of ways to select NPR and the number of ways to arrange R factorial. Okay, so NPR is equal to NCR multiplied with R factorial. Now we will focus on deriving the formula for combination. Okay, so we will look at formula for NCR. So from the relation NPR is equal to NCR into R factorial, from this we can derive the formula for NCR. That is NCR is equal to NPR divided by R factorial. Substituting here NPR equal to N factorial upon N minus R factorial. Here we get NCR is equal to N factorial upon N minus R factorial upon R factorial. And finally, we have derived the formula for combinations. NCR is equal to N factorial upon R factorial times N minus R factorial. Here the condition is given that 0 less than equal to R less than equal to N. Now, we will discuss some properties of combinations. The first property is that NCR is equal to NC N minus R. The second property, which states that NCN is equal to 1 and NC0 is equal to 1. And the property 3 states that if NCA equal to NCB, then either A equal to B or A plus B equal to N. Okay, so you should keep in your mind these three properties. Here, we will look at the proof of property 1. Okay, so property 1 states that NCR is equal to NC N minus R. Okay, let's prove it. So now, let's start the proof of property 1. Take RHS, okay, as NCN minus R and LHS as NCN. Okay, so now we will compare RHS and LHS. So RHS is equal to NCN minus R. Okay, since we know the formula of NCR is equal to N factorial upon R factorial times N minus R factorial. So NCN minus R equal to N factorial upon N minus R factorial times N minus R factorial. And we are simplifying, and it gives us RHS equal to N factorial upon N minus R factorial times R factorial. And this is equal to simply NCR. Okay, and this is equal to LHS. So we obtain here RHS equal to LHS, which was our desired result. Okay, so therefore NCR equal to NC N minus R. Here we will understand this property better with the help of an example. Imagine you have 5 students in a class and you need to choose 2 students for a project. Okay, so in how many ways you can choose them? In method 1, directly selecting 2 students to include, this is 5C2. Okay, selecting 2 from 5. In method 2, selecting 3 students, which automatically results in including 2 students. This is 5C3, meaning selecting 3 from 5. Both methods gives the same result, because when you select 2 students to include, you automatically determine the 3 who are excluded. Okay, and when you select 3 students to exclude, you automatically determine the 2 who are included. Okay, therefore 5C2, this is equal to 5C3. So in general, the rule is when selecting from n items, choosing R items to include. Okay, so choosing n minus R items to exclude. So therefore, NCR is equal to NC n minus R. Here we understand property 2. Okay, here NCN equal to 1 and NC0 equal to 1. So let's look at the proof of this property. So we have for R equal to N. So NCN, this is equal to N factorial upon N factorial times N minus 1, N minus N factorial. Since NCR equal to N factorial upon R factorial times N minus R factorial. And it implies NCN equal to N factorial upon N factorial times 0 factorial. Since we know 0 factorial is 1, so NCN is equal to N factorial upon N factorial. This implies NCN equal to 1. Now let's continue with the proof of the property 2 here. That is NC0 equal to 1. So for R equal to 0, NC0 equal to N factorial upon 0 factorial times N minus 0 factorial. Okay, since NCR equal to N factorial upon R factorial times N minus R factorial. It implies NC0 equal to N factorial upon 0 factorial times N factorial. It implies NC0 equal to N factorial upon N factorial, since 0 factorial is 1. It implies NC0 equal to 1. Okay, so we proved here NCN equal to 1 and NC0 equal to 1. Now we will discuss property 3 of combinations, which states that if NCA equal to NCB, then either A equal to B or A plus B equal to N. So let's prove this property. So we know that the formula NCR equal to N factorial upon R factorial times N minus R factorial. So NCA equal to N factorial upon A factorial times N minus A factorial, and NCB equal to N factorial upon B factorial times N minus B factorial. If NCA equal to NCB, then N factorial upon A factorial times N minus A factorial, this is equal to N factorial upon B factorial times N minus B factorial, and cancel out here N factorial, and we get B factorial times N minus B factorial, this is equal to A factorial times N minus A factorial. And it implies B factorial times N minus B factorial upon A factorial times N minus A factorial, this is 1. So now let's assume B is greater than equal to A. Then we can write B times B minus 1 times dot 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 A plus 1 upon N minus A times N minus A minus 1 times dot 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 N minus B plus 1 equal to 1. Okay. So this equation can only be satisfied in 2 ways. If case 1, if B equal to A, the expression B factorial upon B factorial times N minus B factorial upon A factorial times N minus A factorial, this is equal to A factorial times N minus A factorial upon A factorial times N minus A factorial, become 1. Case 2, if B is greater than A, then the fraction can be 1 only when B times B minus 1 times dot dot A plus 1, this is equal to N minus A times N minus A minus 1 times dot dot N minus B plus 1. And on comparing, we get B equal to N minus A, and it implies A plus B equal to N. So therefore, NCA equal to NCB implies either A equal to B or A plus B equal to N. Clear? I think this property is clear to all of you. Now, look at theorem 6. Okay, theorem 6 is also called Pascal's rule. Okay, so we understand here Pascal's rules, which is NCR plus NCR minus 1 equal to N plus 1 CR. Let's prove this theorem. So take LHS. Okay, so LHS is equal to NCR plus NCR minus 1, and okay, and RHS is N plus 1 CR. So LHS is equal to n factorial upon r factorial times n minus r factorial, since NCR equal to n factorial upon r factorial times n minus r factorial plus n factorial upon r minus 1 factorial times n minus r plus 1 factorial. Taking out common n factorial upon r minus 1 factorial times n minus r factorial, then we get LHS as n factorial upon r minus 1 factorial times n minus r factorial times 1 plus 1 by r plus 1 by n minus r plus 1. This is equal to n factorial upon r minus 1 factorial times n minus r factorial multiplied with n minus r plus 1 plus r divided by r times n minus r plus 1. So LHS will become n factorial upon r minus 1 factorial times n minus r factorial times n plus 1 upon r times n minus r plus 1. This is equal to n plus 1 times n factorial upon r times r minus 1 factorial times n minus r plus 1 times n minus r factorial. This is equal to n plus 1 factorial upon r factorial times n plus 1 minus r factorial. Since n factorial, this is equal to n times n minus 1 factorial. So this is equal to n plus 1 CR and this is RHS. So LHS equal to RHS. So hence proved. Now we will look at example 17. So this example is given where NC9 equal to NC8 and we have to find NC17. So let's find the value of NC17. So let's start the solution of this example. Here we are given NC9 equal to NC8. As you know, NCR equal to n factorial upon r factorial times n minus r factorial. Using this formula, we can write n factorial upon 9 factorial times n minus 9 factorial. This is equal to n factorial upon n minus 8 factorial times 8 factorial. It implies n factorial upon 9 into 8 factorial into n minus 9 factorial. This is equal to n factorial times divided by n minus 8 times n minus 9 factorial times 8 factorial. Cancel out n factorial and n minus 9 factorial, we get 1 by 9 equal to 1 by n minus 8. And it implies n by 8, n minus 8 equal to 9. It implies n equal to 17. Therefore, NC17 equal to 17C17. This is equal to 1. Since NCN equal to 1. Clear? Now, let's look at example 18. So, in this example, we have a community of 3 persons. Okay. So, a community of 3 persons is to be constituted from a group of 2 men and 3 women. In how many ways can this be done? So how many these communities would consist of 1 man and 2 women? Okay, so let's solve this example. So let's start the solution of this example. Given that we need to form community of 3 persons from a group of 2 men and 3 women. The total people 2 men plus 3 women is 5. Okay. So we need to select a community of 3 persons. So what doesn't matter here. So it's combination. Therefore, the total number of ways selecting 3 persons from 5 persons is 5C3. This is equal to 5 factorial upon 3 factorial times 5 minus 3 factorial. Since we know NCR equal to n factorial upon r factorial times n minus r factorial. And this will simplify to 5 factorial upon 3 factorial times 2 factorial. And since n factorial is equal to n times n minus 1 factorial, this is equal to 5 into 4 into 3 factorial upon 2 into 3 factorial. This is equal to 10. Therefore, the number of ways selecting 3 persons from a group of 2 men and 3 women are 10. I hope now it is clear. Now, committees with 1 man and 2 women. So this is a 2-stage process with combinations. Select 1 man from 2 men So that is 2C1 equal to 2 factorial upon 1 factorial into 1 factorial. This is equal to 2. And select 2 women from 3 women. This can be done in 3C2 ways, that is 3 factorial upon 2 factorial into 1 factorial is equal to 3. Therefore, by using multiplication principle, if there are m ways to do one task and n ways to do another task, then there are m into n ways to perform both tasks together. Applying this, total committees with this composition: 1 man from 2 men and 2 women from 3 women. This is 2C1 multiplied with 3C2. This is equal to 2 into 3 equal to 6. So we can list the 6 committees. Each combination has 1 man and 2 women, is basically M1, W1, W2, M1, W1, W3, M1, W2, W3. Okay, M2, W1, W2, M2, W1, W3, M2, W2, W3. Okay, these are 6 combinations. Okay, where it consists 1 man and 2 men. Clear? I hope it's clear to all of you. Now, we will look at example 19. Okay, so here the first part of the example shows how to choose 4 cards from a pack of 52 playing cards. Here we are looking at the number of ways when 4 cards of the same suit. Okay, so let's find. So let's start the solution of this example. So given that 4 cards from a pack of 52 playing cards, where 4 cards are of the same suit. So there will be as many ways of choosing 4 cards from 52 cards as there are combinations of 52 different things taken 4 at a time. So therefore the number of ways choosing 4 cards from 52 cards is 52C4. Okay, and since NCR equal to n factorial upon r factorial times n minus r factorial, so 52C4 equal to 52 factorial upon 4 factorial into 48 factorial. And since we know n factorial is equal to n times n minus 1 factorial, so this will simplify 52 into 51 into 50 into 49 into 48 factorial upon 4 into 3 into 2 into 48 factorial. This is equal to 49 into 25 into 17 into 13. After multiplying, the answer comes 270725. So there are 4 suits: diamond, club, spade, heart. So these are 13 cards of each suit. Okay. So therefore there are 13C4 ways of choosing 4 diamonds, 13C4 ways of choosing 4 clubs, 13C4 ways of choosing 4 spades, 13C4 ways of choosing 4 hearts, so the required number of ways is 4 into 13C4. Okay, so let's now using the formula NCR equal to n factorial upon r factorial times n minus r factorial. So this is equal to 4 times 13 factorial upon 4 factorial into 9 factorial. And since n factorial is equal to n times n minus 1 factorial, so 4 times 13 into 12 into 11 into 10 into 9 factorial upon 4 into 3 factorial into 9 factorial. This is equal to 13 into 12 into 11 into 10 upon 6. This is equal to 13 into 2 into 11 into 10. After multiplying, we get the answer 2860. Okay. So therefore the number of ways of choosing 4 cards from a pack of 52 cards where 4 cards of the same suit is 2860. Now let's look at second part of this example. Okay, so in this part 4 cards belong to 4 different suits. Okay, that we have to find out here. So given that 4 cards from a pack of 52 playing cards where 4 cards belong to 4 different suits. Okay, so there are 13 cards in each suit. Therefore there are 13C1 ways of choosing one card from 13 cards of diamond. 13C1 ways of choosing one card from 13 cards of hearts. And 13C1 ways of choosing one card from 13 cards of clubs. And 13C1 ways of choosing one card from 13 cards of spades. Okay, and hence using the multiplication principle, the required number of ways is 13C1 multiplied with 13C1 multiplied with 13C1 multiplied with 13C1. This is equal to 13 into 13 into 13 into 13. Since 13 NC1 is 1. Okay, NC1 is 1. So 13C1, 13 into 13C2. 13C1 is basically 13 factorial upon 13 minus 2 factorial. Okay, 13 minus 1 factorial into 1 factorial, that is 13. Okay, so this is equal to 13 to the power 4 so 13 to the power 4, and this is equal to 28,561. So therefore, the number of ways of choosing 4 cards from a pack of 52 playing cards where 4 cards belong to 4 different cards is 28,561. Now, we will look at third part of this example. So let's solve this example. So given that 4 cards from a pack of 52 playing cards are face cards. So there are there are 12 face cards and 4 are to be selected out of these 12 cards. So this can be done in 12C4 ways. The required number of ways is 12 factorial upon 4 factorial into 8 factorial. This is equal to 12 into 11 into 10 into 9 into 8 factorial upon 4 factorial into 8 factorial. This is equal to 12 into 11 into 10 into 9 upon 4 into 3 into 2 into 1. This is equal to 11 into 5 into 9. This is equal to 495. Okay. Therefore, the number of ways of choosing 4 cards from a pack of 52 playing cards or face cards is 495. So now let's move to the next part. Now we will find the number of ways of choosing 4 cards from a pack of 52 playing cards to so that 2 are red cards and 2 are black cards. Let's solve this part. Given that 4 cards from a pack of 52 playing cards where 2 are red cards and 2 are black cards. So here you know the multiplication principle. So if there are m ways to do one task and n ways to do another task, then there are m into n ways to perform both tasks. Since there we have 26 red cards and 26 black cards, so 2 cards from 26 red cards and we will select 2 cards from 26 black cards. Okay, so total number of required number of ways is 26C2 into 26C2. This is your 20 factorial 26 factorial upon 2 factorial into 24 factorial whole square. This is equal to 26 into 25 into 24 factorial upon 2 factorial into 24 factorial whole square. This is your 26 into 25 upon 2 whole square. This is your 325 whole square. This is equal to 105625. Therefore, the number of ways of choosing 4 cards from a pack of 52 playing cards where 2 are red and 2 are black cards are 105625. Now, let's look at the fifth part of this example. Let's solve this part of this example. So given that 4 cards from a pack of 52 playing cards, the cards are of the same color. The 4 red cards can be selected from 26 red cards and or 26 black cards. So 4 red cards can be selected out of 26 red cards in 26C4 ways. And 4 black cards can be selected out of 26 black cards in 26C4 ways. So therefore, by addition principle, so addition principle states that if there are two jobs which can be performed independently in m and n ways respectively, then either of two jobs can be performed in m plus n ways. So the required number of ways is 2064 plus 26C4. This is equal to 2 times 26 factorial upon 4 factorial into 22 factorial. So this is equal to 2 into 26 into 25 into 24 into 23 into 22 factorial upon 4 factorial into 22 factorial, since n factorial is equal to n into n minus 1 factorial. This is equal to 2 into 26 into 25 into 24 into 23 upon 4 into 3 into 21. This is equal to 26 into 25 into 12 into 23 is equal to 29,900. So therefore, the number of ways of choosing 4 cards from a pack of 52 playing cards are of the same color is 29,900. Okay, I hope it's clear to all of you. So students, that's all for today's lecture, and thank you very much to all of you.